All right, everybody. So I wanted to do a quick lecture about predation. This is chapter 12 in your textbook. And towards the end, I'll discuss some of the other activities and work that I want you guys to do. So to start out with, just remember that there are these key concepts in your from your textbook. Most carnivores have broad diets, whereas the majority of herbivores have relatively narrow diets. We'll talk about that and why. Predation results in a wide range of capture and avoidance mechanisms. We'll talk about some of those. Predator populations can cycle with their prey populations, and I have an activity for you guys to do with that in Excel. And then predation can affect prey distribution and abundance, and in some cases cause a shift from one community type to another. And I have a paper that I'd like for you to read related to that. All right, so there are various forms of predation, and simply predation is individuals of one species as a predator will feed on and directly harm individuals of another species, and that would be the prey. So the forms are carnivory, herbivory, and parasitism. And carnivory is a predator and prey are animals. Herbivory, the predator is the animal, and prey are plants or algae. And not all organisms fit neatly into these categories. So you can think about some carnivores, for example, such as wolves, also eat berries, nuts, and leaves. And there are also these various forms of plants that are carnivorous plants, as an example, Venus flytrap, a pitcher plant, and a sundew. Other what are typically thought of as carnivores will sometimes eat be more herbivorous at times as well. Bears is another example. And in parasitism, so this is when the predator is a parasite, lives symbiotically on or in its prey, and that is the host, and it consumes certain tissues and may or may not kill the host. Some parasites can be pathogenic, of course. And then there are parasitoids, and these are those that lay eggs in or on another insect host, and after hatching, the larvae remain on the host or in the host, which they eat and usually kill. And so over here on the right side of the screen, you can see is an example. This is an ichneummonid wasp, which are parasitic wasps, and they lay eggs inside caterpillars. And eventually the larvae hatch inside the caterpillar, and they will then pupate on the outside of the host caterpillar. So these are a bunch of eggs of some sort of ichneummonid wasp species. And then they hatch out of there, of course, and fly away. Science reality is much more interesting than science fiction, at least most of the time. So carnivory versus herbivory. Carnivores kill their prey. Herbivores usually don't kill their plants that they eat, although they can, depending on the situation. Animal prey usually move away from or hide from predators, but however, of course, plants cannot do this, and so plants will develop different strategies to try to keep from being eaten. We'll talk about some of those. And then plant prey are often more abundant as they have lower nitrogen content and less nutritious than animal prey. In the figure down below, you see that the nitrogen content in animals is much higher, but also has a lower lower variability than, for example, leaves, and then also phloem and xylem sap. And this is important because the amount of nitrogen in things that you eat are needed for building body parts in DNA and things of that nature, various nitrogenous compounds. Optimal foraging theory, we talked about this, or you read about this in one of your other chapters. And so optimal foraging theory and dietary preferences depend on the encounter rate, so how often an organism comes into contact with its prey. And if this is low, predators, carnivores should be generalists. In other words, if they have a low chance of running into something to eat, then they should just eat whenever they find something. And so a lot of carnivores, for this reason, will eat pretty much what they run into and have a wide range in their diet. And then handling time is the other component of optimal foraging theory. And if prey are easy to find, but handling time is long, in other words, they're immobile but less nutritious plants. And when we talk about handling time, you can think not only about the time it takes to actually eat the thing, but also the time it takes to digest it and that type of thing. So then if this is true, then the predators, the herbivores, should be specialists. So they should identify some plant that is palatable to them, so to speak, and they have evolved a sort of a relationship with that they are it's more easy for them to digest. and get as much nutrition out of that plant as possible. And so based on this information, would you expect carnivores to be generalists or specialists? And the same for herbivores. And we've already talked about that a little bit. So carnivores, of course, tend to be generalists. They prey in relation to their availability without showing a preference for any particular prey. However, there are, of course, exceptions. Some carnivores show a preference. So, for example, lynx eat more hares than would they normally be expected based on hair abundance, and using optimal foraging theory as a foundation for testing that. And then some carnivores concentrate on whatever prey is most abundant, so they can actually sort of switch. And you can see this in the figure on the right here, where in the lower portion of the figure, when the percentage of prey that are worms versus the percentage of worms that are in the diet, when that is low, when the percentage of prey are available are low, then they have low percentage of worms in their diet. And so as that increases, as there become more and more availability of worms, then they switch to eating more of the worms. And then herbivores. So herbivores tend to be specialists. Let's see here. Yes. See if this will load. I always have trouble with these things loading in my PowerPoints. But, so most herbivores tend to be specialists. Large herbivores may eat all above ground parts, but most specialize on particular parts. So for example, leaves, stems, roots, seeds, or sap. And you can think about organisms that eat different components of the plant. So a lot of browsers will eat leaves, for example. And I have supposed to have a video of a moose down here. Maybe I'll just pull it in from over here. You guys can see, and you watch this moose, how it eats. This, I think, is a willow shoot. So it just strips that right off. It's pretty cool. So that's how moose actually eat. And so they've sort of specialized on leaves, of course. And then leaves are most commonly eaten because they're often the most abundant and also the most nutritious part, of course, other than seeds. And so things that eat seeds would be things like birds and some other animals. And of course, herbivores can reduce the growth, survival, and reproduction of plants. Most insect herbivores will only feed on one or a few plant species. Of course, there are exceptions to that. Some herbivores, such as grasshoppers, feed on a wide range of species. And large browsers, such as deer, often switch from one tree or shrub species to another. And the picture that you see in the bottom there is a grove of aspen trees that have been chewed on by elk. This is typical in the winter months when there's low availability for other things to eat. So they come in and chew on the bark of the aspen trees. And so they can switch from eating what they would normally eat, sort of leaves and that type of thing, over to switching to eating things such as bark, which are much less nutritious, of course. And then mechanisms for predation. Basically here, the organism's trying to increase its chances of eating. And many carnivores forage by moving about in search of prey. So you can think about wolves, sharks, hawks. Those things are constantly on the move and they're sort of searching for prey. And then others might remain in place and attack prey that come within striking distance. Examples would be some fish species, there's moray eels. And then down here in the bottom left, you see this is a bowfin, and they're a really good line weight predator. And you can see a lot of times the structure of the organisms, the shape, will sort of dictate or its type of predation that it does. So these guys are really sort of flat bodies, broad bodies, and they sit and wait, hiding somewhat, and then they're very explosive over a very short span so they can capture their prey. And then, of course, others set traps, such as spider webs or modified leaves of carnivorous plants. And you can see also this is a type of mantid, and they can have this camouflage coloration that allows them to be really good sit and wait predators. And then this is an example of an antlion. Antlions are these, you may have seen these little, in really dry dirt. A lot of times you'll see these little conical shaped depressions in the dirt. And there's actually a little organism, a little insect down in the bottom there that waits for ants to come into their little trap, and when they feel that the ant is crawling around in there, they'll actually throw dirt up into the cone, and it makes it difficult, sort of slippery for the ant to get out, and they can capture and eat the ant. Those are pretty neat videos if you are interested and haven't seen those guys work before. And then there are other mechanisms, of course. There are physical features that help capture the prey to be captured. And those can be body shapes, or for example, cheetahs' bodies enable them to have high bursts of speeds to catch gazelles, which are also similarly shaped. And then snakes can swallow prey that are larger than their heads because their skull bones are not rigidly attached to one another as most other vertebrates are. And just as an aside, your book says this, that if you could dislocate your jaw and swallow something the size that a snake can, you could swallow a watermelon whole. I'd heard previously a bowling ball, but regardless, that's pretty impressive. There are other mechanisms, of course. Some predators subdue their prey with poisons. You can think about spiders. Some use mimicry. In other words, they blend into their environment. So to be the prey are unaware of their presence or camouflaging. And then some predators can detoxify or tolerate chemicals made by their prey. So for example, a western species of garter snake can tolerate a really toxic newt, and I think it's also the western newt. And the newts actually, I believe, are the most toxic organism on Earth. They can have enough toxin to kill like 25,000 mice in one organism. There have been stories of people trying to eat them and dying, and some of them crawling into coffee pots and people pouring coffee that had the toxin in it and them dying, things of that nature. I don't know if they're true or not, but anyway. And then there are mechanisms that are things like physical features. So you can think about size as a physical feature to avoid being eaten, like an elephant or giraffe or cow or something like that. Things that are really big, and they sort of depend on that as part of their overcoming being eaten. Speed, so animals that are really fast. Pronghorn antelope is a good example. Gazelles, things of that nature. And then there are, of course, armored animals that have some form of armor that allow them to keep to avoid being eaten. And armadillos is something that comes to mind. Turtles, things like that. Then there is this aposematic coloration or warning coloration, and this really depends on a learned behavior of the predator. So the predators must learn that there is that these things are not tasty and you can't eat them. So it may not make sense for the organism to kill its predator, but it also needs to be toxic enough that the species will release it. And an example, you see the butterflies down here, the monarch and viceroy butterflies. That would be sort of an example of a warning coloration where a species might, I think birds like jays, corvids are known to eat or try to eat these guys and learn quickly that they're not very tasty. So that would be an example. And then cryptic coloration, this is where organisms sort of blend into the background. And you can see up here on the right, there is actually a lizard in this picture. It's really difficult to see, so it's really well camouflaged, has this really good crypsis. You can think of lots of other organisms that have this coloration, this cryptic coloration. And then mimicry. And in mimicry, these organisms resemble another toxic or aggressive organism. There are two forms of mimicry. There's Batesian mimicry, and this is when the mimic of one organism mimics a harmful or noxious species. And so an example would be a lot of flies. As you see here, this is a fly and this is a honeybee. They look very similar, so a lot of times things that fly around and people think are bees are actually just a fly. Another example would be a coral snake and a king snake. And so the scarlet king snake looks very similar to this coral snake, and so that is a form of Batesian mimicry. And then the other type of mimicry is Mullerian mimicry, and this is when two equally noxious species evolve to look very similar in this sort of convergent evolution. And so you can think about most bees and wasps look very similar, okay? And so they have this sort of common coloration that allows other organisms to avoid them. And then I guess just learned this, that the monarch and viceroy both are sort of noxious tasting to birds, and so it was formerly thought that this was a form of Batesian mimicry, where the monarch was noxious and the viceroy was not, but this is apparently a form of Mullerian mimicry as well. On to plant defenses. Some plants produce huge numbers of seeds in some years and hardly any in others. This is called masting. And this is basically sort of the plant's ability to, quote, hide in time from seed-eating herbivores, and they can then overwhelm the herbivores with the sheer number of seeds that are released. In other words, the herbivores can't eat them all. So you can think about organisms that do that. I think your book references a plant that, I can't remember where it is, maybe India, but it only releases its seeds on every 100 years, and so that's pretty impressive. Some plants have adaptive growth responses that allow them to tolerate herbivory, and so this would be sort of a compensatory growth. And so in compensation, the removal of the plant tissue stimulates new growth, and the plant can have full compensation, in other words, no net loss in plant tissue through this process. And then plants have some structural defenses. In other words, they have sometimes tough leaves or noxious leaves, they have spines, they have thorns, saw-like edges, pernicious or nearly invisible hairs that can pierce the skin. Some of you may have experienced that with stinging nettle in a lot of moist creekside areas. Some are induced defenses that produce a response due to the herbivory attack. So, for example, some cacti will increase spine production after being grazed. And then secondary compounds are also a product that plants can use. And these are toxic chemicals that reduce herbivory. And some of these compounds will actually attract predators or parasitoids that will then attack the herbivores. So that's a pretty neat adaptation. And then some are produced all the time. So you can think about, for example, oak trees have a sort of a noxious taste, and they're produced all the time. And then others can be induced through herbivory. All right, so that's the end of the presentation. I'm going to send out also this more Excel work to look at predator-prey cycles, and I'll just have you sort of change some values in the Excel sheet, and you can answer some questions related to that. And then there's a journal article that I'll have you read about predation and community structure. All right, we'll see you guys back here soon.